Hi everyone, Barbut. Thank you for being here. Sorry to interrupt me. We have to get started. I will tell you about collective light-matter interactions in atomic ensembles. So this is a very general title, and then we'll tell you in more details what kind of light-matter interactions we have. I work at Institut, which is very close to here. You've seen the talk of Antoine in the same group, in the quantum optics group. You've seen this picture before. Antoine told us about the work of the group on Rydberg atoms. He said it's non-dissipative in their case, or dissipation is unwanted. And I will tell you about the work that is done in the two teams that are studying light scattering, which in a way is doing quantum many-body physics, but with dissipation, where dissipation is something that you look at and that you're interested in. So let me tell you in a bit more details simply what we do. In the group, you heard that we're able to isolate two-level atoms, a single one or many, isolate them in optical tweezers, put them in free space. What we do in my part of the group is to study their response to resonant light. For a single atom, this is very well known. You know, if you can isolate the two-level system within the atom and you send resonant light, you know what's happening. Optical Bloch equations tell you the dynamics. You can calculate photon-photon correlation functions quite easily. And in a nutshell, what we're doing in the group is now to say, okay, I can put one, but I can put many of these atoms and study their collective response and try to understand whether the collective response differs from the single atom response and whether there are interesting collective effects that emerge that you don't find in the single atom case. Okay, so historically, you can see this as a light scattering problem, something that's more into light matter interactions. But now you can reframe this in the words of many-body physics, which is kind of our background, which is to say that you have a single spin or a two-level system, qubits, that interact with each other and that have collective dissipation. So you can see this as a dissipative spin system. Okay, so it's a hard many-body problem, of course, because the system is going to explore the whole Hilbert space. So it's challenging to describe with dissipation. So you need approximations. Of course, we know, maybe some of you know the seminal work of Dickey, who used an approximation to say that the ensemble stays in the symmetric states with respect to permutation symmetry, in which case you can study what happens, at least theoretically, and you get one phenomenon which is called superradiance. So we'll come back to this. But of course, we need experiments to kind of benchmark theories. We do this just fundamental physics. It's hard fundamental physics, but we have also motivations for quantum technologies. There could be interesting applications of collective like-matter interactions. For instance, in particular in quantum technology for light storage or interesting interfaces. So there are many proposals and now experiments that are performed in this direction. So before showing you the experiments, I just want to set the theoretical frame. I guess because there are many theoreticians in the room, maybe this will make things clearer. So when you study the dynamics of an ensemble of two-level atoms interacting with light, you have a master equation. So classically, what you have is each atom is a radiating dipole. So you send resonant light, the dipole oscillates, it radiates a field, and now the atoms nearby will feel the field of the laser that's driving and that of the atoms around it. Okay? So you will have classically a system of coupled dipoles. Okay? And now, of course, these atoms are not linear dipoles, but they can be saturated. They're two-level atoms, so you have to write the master equation, but the coupling is the same. So in the master equation, you have a real part, which is a spin exchange term between one atom and the next, and the coupling between these two atoms is given by the real part of the dipole-dipole interaction that you would get of the field that's radiated from one atom to the next. Okay, and what you get, which we didn't have, for instance, in the talk of Antoine with atoms, is a dissipative part as well. So one way to see it is if you have two atoms that are exactly on top of each other, you look far away. If they are oscillating in phase, in fact, the dipole is twice bigger, the field is twice bigger, the intensity is then 4 times larger, which means that they dissipate faster, okay? So you have somehow a collective dissipation. If on the opposite, you put them exactly out of phase with respect to each other, 0 dipole, 0 dissipation. So the master equation has some collective jump operators, if you want. You have jump operators that couple atoms with each other. You can diagonalize the Lindbladian to get the collective jump operators. So this is the master equation in all generality that describes the experiment that we do when we have atoms in free space that interact with each other via resonant light that we excite them with. So of course you also have driving in this problem. Each atom is driven by the resonant light, but it's also driven by the light of the other atoms. And then experimentally, what do we have as observables? When we do light scattering, in general, we look at the light that is radiated by the cloud. So if you look at the intensity, it's the square of the field. The field is the sum of the jump operators, the probability that a photon has emitted, was emitted by an atom, times the Green's function, the propagation of the photon in the place of the atom to where your detector is. So when you sum, you have a double sum over all atoms. So you see that the intensity, the radiated field that you get is given by atomic correlations inside the ensemble. So that is, if you look at intensity, you will see that when we look at the photon-photon correlation function, you have a different sum over atomic observables, but you always have in these free space atomic ensemble a very simple relation between the field degrees of freedom that you can measure and the atomic degrees of freedom that you have in the ensemble. So this tells us that actually, as experimentalists, we might have two probes to study the system. We might look at the radiated field, look at the photons, measure the photons, but you've seen before in other talks that you can also measure the atomic degrees of freedom. Now with quantum simulation, you're able to measure directly the state of the atoms. And this is why in the group we have two experiments now, two teams that kind of look at these two observables. So we have one experiment that I will first talk about, which produces large atom numbers, thousands of atoms. So you don't have, it's a disordered system, you don't have the possibility to look at the state of single atoms, but then you have many photons that are emitted, and you can detect these photons and look at the field degree of freedom, intensity, photon correlation, etc. So you can look at the dynamics of intensity, for instance. This is what I represented here. And then we have another experiment, which is under construction, that is coming online, where we actually produce arrays of single atoms, and then we perform light scattering, but we have access, exactly like on the Rydberg setups, to the state of individual atoms. We can measure the individual state. We can take a snapshot of the atomic state at a given time. So first, I will start with the dense cloud, and hopefully I will have a little bit of time to show you the progress of the other setup. So on dense cloud, I will present work that was mostly done by Giovanni, who was a postdoc with us. And now the experiment actually has been taken over and is being rebuilt by 3 graduate students that you see here. Oh, okay, so just tell you a bit more in details what is the experiment doing. So you've seen that we were trapping single atoms in optical tweezers, but by changing a bit the parameters of your optical tweezer, actually you can put it in a regime where you can put hundreds to thousands of atoms inside the optical tweezer. And the advantage of these optical tweezers is that they have a very small volume, so you can put thousands of atoms within a volume that's not very large in particular with respect to the wavelength of the transition when you to light scattering, the relevant length scale to know whether atoms are interacting strongly or not is the wavelength of the transition. If you look at the dipole-dipole interaction, the only length scale that you have is the wavelength. So in our clouds, they have an elongated shape like this. There are a few microns along their long axis. So this means that this is a few times the wavelength. Okay, where the wavelength is that of, these are rubidium clouds, so the wavelength is 780 nanometers. And radially, these clouds are very small. They are roughly on the order of the wavelength or smaller. So this means that they have, with respect to light scattering, some interesting properties. For instance, if you detect a photon that's emitted radially with respect to the cloud, so perpendicularly to the long axis, it means that if you have a high resolution microscope like we have aspheric lenses, it means that essentially you can resolve where it was sent from, okay? So it means that it was not sent collectively by all of the cloud. It was sent by one atom in particular along this cloud because you can resolve it. But on the other hand, if you send a photon along the cloud axis, there is nothing that tells you which atom emitted it. And so you really have a collective coupling. So you have one mode. This mode is basically the diffraction mode of the cloud. It's a Gaussian mode that has a Rayleigh length that is the length of the cloud. And if a photon is emitted in this mode, it was collectively emitted by the cloud. There is no way to tell. So you have then a jump operator for the emission of this photon, which is a collective one, a superposition. So when one photon is emitted, you keep the cloud in a superposition state. Okay, so you have a symmetry that remains in this system. And if you know a little bit the language of cavities, in fact, what you have is you calculate the power that the cloud radiates in this direction, roughly, divided by the power that you would radiate in 4 pi. And this will tell you the cooperativity of the cloud. So of course, the single atom cooperativity is 0. It's 10 to the minus 2, 10 to the minus 3. But when you put hundreds or thousands of atoms, at some point, your collective cooperativity becomes larger than 1, and atoms are collectively coupled to this. You have cooperative emission in this direction. So with these clouds, we've done a few studies, especially of collective spontaneous emission. So we've studied, for instance, Dickey superradiance, which is you invert fully the system, and then, as I told you, you stay in the symmetric states according to Dickey. Here, it's not exactly the same because you have only a single mode, but you still have Dickey superradiance, which we observed. We've studied also the driven case where you continuously drive the system, looked at the steady state and observed in particular steady state superradiance. We've also looked at subradiance where you see that you excite the system, you let the excitations decay, and at some point, the excitations take longer and longer to escape the cloud. And this is because you've created a state within the ensemble that has destructive interferences in the field that it emits. So it's more favorable to keep the excitation inside. And what I want to show you today is the last experiments that we published, which is going beyond looking at light intensity, not only looking at the number of photons per unit time that you emit, but doing actually what we should be doing as a quantum optics group, looking at quantum optical observables, in particular the G2 function of the light. Okay, so the G2 is intensity correlation, or in terms of number of photons, it's just the number of photons that you detected at time t and at time t plus tau divided by the number of photons that you have at time t times the number of photons that you have at time t. Okay, so for single atoms, actually, what you have is that the G2 function of a single atom at t is equal to 0 is equal to 0. Okay, this was a milestone of quantum optics. Why is it equal to 0? But well, you have an atom that's driven by light, so its Bloch vector is doing whatever it does under optical Bloch equations. At some point, you emit a photon, you have a quantum jump. You will reinitialize the state in the ground state, so you cannot have a second photon emitted. You have to wait for the Bloch vector to oscillate again. This is why you see these optical these Rabi oscillations in the G2 function.
What's the meaning of C equals 0?
The meaning of it's tau is equal to 0 in this So the meaning of tau is the probability to detect 2 photons at the same time divided by the square of the probability of detecting 1 photon at this time. So you're looking at whether the fact that you already detected a photon will modify the probability that you detect the second one. Okay, so tau is equal to 0 is what is the probability to have 2 photons at the same time. So this tells you that you have 0 probability. And this is because you have a single atom, it cannot emit twice at the same time. But of course, now in our clouds, we have many atoms. Okay, so this picture will be modified because 1 photon is emitted, but you don't know what happens for the next photon. You might emit a second photon exactly at the same time. So experimentally, as I told you, you count the number of clicks that you have on photodiodes and divide this by the average number of clicks at these times. It's a very standard setup to measure G2. So let's talk about many atoms now, because one single atom is pretty clear. When you have many atoms, of course, it becomes extremely challenging because you have to calculate these operators. So you have to sum over the whole state. So you don't know the state of the system. It's way too hard. So one well-known formula is to assume that your emitters are completely decorrelated, that they don't have the same phase at all. So you can even take them classical, or it works also for atomic emitters. And what you get is if you have phase decorrelation, is that the G2 function of the light is 1 plus the first order coherence G1 squared. Okay, so here you assume that your emitters are completely uncorrelated. And actually, in dense clouds, this was verified. For instance, there is a lot of work by the group of Robin Kaiser and Mathilde Hugbard in Nice. And this is an experiment here that we've done where you prepare a dilute cloud. So in our case, we let the atoms expand, we put them very far away from each other, we make them move so that they are completely decorrelated. And then you recover perfectly G2, which is exactly equal to 1 plus G1 squared. You see you see Rabi oscillations. For experts, this is the Fourier transform of the Moller triplet. Okay, you're looking in time, and if you take the Fourier transform, you will look in frequency, and you will see the Moller triplet. We see exactly G2 of 0, which is equal to 2, so we have no experimental imperfections. Why do you see G2 of 0, which is equal to 2 in this case? But this is a Hamburg-Brown twist. You have if you want bosonic bunching at t is equal to 0. And now let's do it in these small clouds that are super radiant. So if we look perpendicularly to the cloud axis, in fact, here we see no effect. We still, it's a noisy data, but we don't see any modification with respect to the predictions of the Ziegert relation. And in a way, this is expected, if you want, because we know that these emitters are really independent from each other. They don't have any phase correlation. The laser is not propagating along the direction in which we drive them. So we didn't put them in phase with respect to each other. So when you look at fluorescence, there is no reason why you should get anything different from an uncorrelated cloud, and this is what we get. But now the big difference comes when you look along the cloud axis, where the atoms are emitting collectively, and there what we see is a modification of the G2 function of the light. You see in particular a reduction with respect to 2. Okay, at t is equal to 0, you have a relatively large reduction, and we even have times where G2 of tau is smaller than 1. Okay, so why is that so? Well, it's relatively challenging to calculate, as I said, because you have to calculate the state of this many-body system in order to calculate the average value of the field to the 4th power. And of course, we have, as I told you, thousands of atoms. So there is no way that you're going to solve the dynamics exactly. Okay, so you have to resort to approximations. And in fact, there was a nice trick that was found in particular by Giovanni, which is to say, I don't know
the state of the system, but actually this data tells us the level of correlations that we have in the ensemble. This is not the most strongly correlated system ever, but actually, just by looking at this data, I can tell you that you have non-Gaussian correlations inside the ensemble, and I will just run through the argument. I don't have too much time to show everything, but basically, the Ziegert relation can be derived by assuming Gaussian statistics. So the only order of correlations that you keep are second order, and all higher order cumulants or connected correlations, depending on your language, you assume them to be zero. So you have a Gaussian density matrix. And then in this case, you derive, if you make this assumption, you get this relation, you apply this to calculate G2, what you get is G2 is equal to 1 plus G1 squared plus some terms that I don't have time to tell you why, but we know that there is no mean value of the field. So we know that we can eliminate these terms. Anyway, this one, maybe you want to keep it, but if you see a reduction, it cannot be explained here because this is always positive, okay? So what we see is that if you have Gaussian statistics, then you necessarily have G2 of tau, which is equal to 1 plus G1 squared, plus maybe something higher, but when we see a reduction, we know that the assumption that you have Gaussian statistics is violated, okay? So what we observe is that the driven dissipative dynamics is hard, it's challenging to describe, and we see that you can't do a cumulant expansion where you stop at order 2. This will not work, this will never be able to describe our experiments, okay? Which was not the case, for instance, when we looked at superradiance. When you look only at intensity, you have order 2 correlators, and in this case, with colleagues, Francis Robichaud in particular, cumulant expansions stopping at order 2 was working. But in our case, for the G2 function, we know that you have to go higher than this. And so at the moment, this is the level at which we are. We know that you have interesting correlations that emerge. For us, it's kind of interesting because sometimes to actually engineer correlations in a many-body system is relatively challenging. But here we just take a cloud of atoms in free space, shine light on it, and we're able to say, okay, there are interesting correlations that show up. So we want to gain a bit of control on this because we all know that non-Gaussian states are interesting. So in the last 2 minutes that I have, I will just flash the work of the dysprosium team, who is doing the same thing, but now building an experiment where you have the ability not to look at the photons, but to look at the state of the atoms of themselves. Because on the other experiment, we look at photons and we infer something about the density matrix of the system. But now, why not looking directly at the system? So this is done by Damien, Breton, Nathan, and Julie, who is today in the room. And so in this experiment, we produce arrays of single atoms. So we chose dysprosium. You saw the talk by Antoine where it was rubidium. So we built the tools of single atom trapping and imaging for dysprosium, and we chose dysprosium in particular because you have this level structure which is extremely complicated, but there are symmetries still, so you can still do physics and do light scattering in particular. So you can, for instance, isolate a three-level system where you have one transition which will be relatively narrow, where you do your light scattering, and you have a very broad transition, and this very broad transition allows you to measure very fast the state of the system. Okay, so essentially we do light scattering on a given transition, but we have a stronger probe that allows us to project the atoms either in the ground or in the excited state and measure their state. So you can do like this by this projective measurement. You can image, for instance, I don't have time to explain the detail, but you can image the population during optical Bloch equations, where you see here the single atom decay, and you can measure the population like this under driving. So just to flash preliminary data that we have on this, what we do is we prepare a chain of atoms like this, and we shine light along the chain, and this has the interesting property that the interaction the light-mediated interaction between the atoms, you always have this propagation factor exponential ikx. But what's interesting here is that if you shine light along the axis, you have a factorization of this propagation factor. So the interaction between the atoms, even if the atoms are relatively far from each other, are in phase with respect to each other. So you have constructive interference in the collective light matter interaction. So even if you have a very small chain with atoms that are at the distance larger than the wavelength, actually you see collective effects. So for instance, if you measure the shift of the propagation, which is the maximum of fluorescence as a function of frequency, you see a collective shift as a function of the distance. So with optical tweezers, you can very easily change the distance between your atoms. So we start to see collective effects. We start to have now the possibility to measure which atom is in the excited state and which atom is in the ground state. So we can measure the probability for the atom to be excited or not. And we see that this probability, it's noisy, but it evolves as a function of position. So for instance, you see that for some detuning, actually the last atoms have less of a probability to be excited because they are, if you want, in the shadow. This is the microscopic view of the Beer-Lambert law. And if you have actually an opposite detuning, you have an opposite effect, which is the atoms at the beginning of the chain enhance the probability. If you want, they create a lens that increase the field at the position of the last atom. So we see an enhanced probability for the atom to be excited. So with this, I will stop without telling you much more the future. This is the group that done the work, and thank you for listening.
I have a few questions actually, if I can, about the first part. So you said the electric field is equal to 0. Is it because you don't have coherences between states with different number of photons, or it's?
So the electric field. So the formula of the electric field is that it's the jump operator on a given atom times the propagation. So we have several ways. So the first thing that you can do is measure the G1, first order coherence. And if your first order coherence goes to 0 at long times, this is the average value of the field. And we've measured that it does go to 0 at long time. So we know that the average value of the field is 0. We have other ways because if you look at the intensity, for instance, if you have if this is not 0, it means that your intensity scales at the square of the atom number because the field is linear in the atom number. So and it doesn't scale the square, but it scales linearly with the field. So we have two ways of saying that in fact the average value of the field is 0. But I don't believe that this will always be the case. At some point in the steady state, you might build up coherence, which we didn't see in our experiments. Maybe if you increase the atom number, I think it might happen.
And if I can, the second question is, I mean, this probes basically non-Gaussian properties in the electric field.
Yes.
Of the but you have a matter part also. What
Yes.
you know
So
about
I was a bit fast, but because the field
for atoms.
because the field is a linear superposition of atomic degrees of freedom, you know that the atomic degrees of freedom are non-Gaussian as well.
Okay.
For instance, if you measure a Gaussian field, this doesn't tell you that the atomic state is Gaussian.
Okay.
But if you measure a non-Gaussian field, you for sure know that the atomic state is non-Gaussian. Yes?
So a question for the second part, is positional disorder possible in your chain? And did you think about this as giving rise to interesting localization type physics potentially?
Yes. So it's possible because these are optical tweezers, so you can really set the position exactly as you want. And so there are proposals for experiments to do Anderson localization, for instance, in 3D. And not necessarily in tweezers, but you can also do it in optical lattices where you can have diagonal disorder or positional disorder. In our case, I believe the systems are relatively small, so I don't expect it to be strong. But anyway, you have positional disorder, as Antoine explained, because even if the tweezer is very well localized, within the tweezer, the atom is not perfectly localized, so we might have these effects. But I don't think that we are in a regime where you expect strong localization.
Okay, thank you.
Thank you.
And what are the distances here?
Uh,
Compared to the.
Let's say it, no, it's about 1.5 times the wavelength. So it's about 1 micron and the wavelength is 626. This is the next step. Is to